Hey everybody. So continuing our discussions on automation, today we're going to be covering automating the hot side of the brewery. The picture here is actually not a brewery. This is the control room for a nuclear power plant, but I just thought it looked cool and kind of the look we're going for here. So here's my current brewery setup. Pretty standard 3-tank system. You've got a hot liquor tank on the right, mash tun in the middle, boil kettle on the left. So the goal here is we want to build a control panel that integrates with our software that controls a heater inside the hot liquor tank, another heater inside the boil kettle, and then we have 2 DC pumps to control. They're sitting there on the shelf. And then we have 3 temperature probes, 1 for each tank. And we have a flow meter, which is kind of hard to see. It's kind of hidden by one of the hoses. I'll show another picture of that later. So how do we go about deciding what we need in the panel to power and control all of this? So as last time, we're going to be focusing on Arduino-based microcontroller systems here that integrate with brew control, but you can use the same techniques to integrate with any software you like, especially if you decide to do something like write your own firmware for the Arduino. So here's the control panel. And I'll go into more detail about each of these components later, but just kind of an overview of what the finished, or pretty close to finished, panel looks like. Right now, it's just sitting on the lower bench. Eventually, I'll have this nice and wall mounted, but I'm still doing some final testing. When you're deciding how to build one of these out, this is one of the more important laws, especially when considering things like AC heating elements on the hot side. So let's say you picked up a couple heating elements. Well, how do you decide how much amperage you need to power them and how much is going to be left over for the rest of your panel to use? Pretty important question. So Watt's law states that power in watts equals voltage times the current in amps. And to put that in a little more kind of practical terms, we can say heating power, the power consumed by our heating elements in watts, is equal to our circuit voltage, which is either going to be 120 or 240, depending on your circuit, times the amperage of that circuit. 30 amps, 50 amps, 20 amps. So the example that I'm going to use is kind of my thought process in designing this part of my panel. So at first, I started out with 2 5,500 watt heating elements. And these are on a 240 volt circuit. Now, doing the math out on these, if we solve for if we solve for the amps that these are going to end up consuming on the circuit, we have 11K divided by the voltage 240. That, rounding up, is about 46 amps. If we have a 50 amp circuit, that doesn't leave us with very much play for other components that we might have in the system. Have pumps, we're going to have sensors, we've had the microcontroller, etc. So one decision I made is I thought to myself, well, my boil kettle, I'm generally starting out my boil with 7 gallons, give or take, because I'm normally doing 5-gallon batches. Sometimes I do a 10-gallon batch. More often than not, it's just 5, so my starting volume for the boil is only 7 gallons. After looking around a bit, I determined it was perfectly feasible to go down to 4,500 watts for that particular heating element. Now, a new hot liquor tank I'm beginning to integrate now, which wasn't pictured earlier, is 26 gallons. So for that, I definitely want to stick with the full 5,500 watt element. So making this compromise, this actually gives me 5,500 plus 4,500. We math that out, solve for I, we get about 42, and this is rounded up, so 42 amps. And now we have a pretty good amount of space, 8 amps for the rest of the system, which seems a little bit more reasonable. So if we have a dedicated 50 amp circuit, that means there's nothing else on it besides our control panel. Then 42 amps, as we just calculated, would be used by these two heating elements in this particular example. And that's assuming, of course, they're both on at the same time. Then we have 8 amps remaining for everything else. Probably the main consideration for most systems like this will be the pumps and the power supply itself. These are going to consume together most of the rest of the amperage that's left over. In my case, these are pretty small DC pumps. They only consume 1.5 amps, even running at full bore. So that's 3 amps plus another 2, assuming the power supply is really ramped up. That still leaves us with pretty good headroom for our sensors and microcontroller, which consume very little amperage. So looking back at the panel implementation, there's some things to think about here. So direct your attention down here. Here we have our 2 plugs for the heaters, and each of these are capable of delivering 30 amps. Of course, not that much is ever going to go across these. It'll be less than 25 for each of them at all times. But these are the types of plugs that if you go and buy one of these electric homebrew heating elements, this is what you'll need to have. So these are attached to the bottom, and we'll get a closer look at how they integrate in a second here. And then another important consideration is this guy. This is a hardware kill switch for the high voltage part of the panel. So in the case of software failure or a sensor failure, we don't want the heating elements to come on when we don't intend for them to come on. That could be really dangerous. We don't want them to dry fire. So it's good to have this clicked off until you're in a state where you know that you want the software to switch these on and off. Then here we have the plugs for the 2 DC pumps. And then here we have a port which we have our 3 one-wire temperature probes coming out of here. And then one additional, this black wire is the wire for the flow meter. Okay, so back to the top of the panel. Here's where we have our 50 amp circuit incoming. And this is going into a terminal block here where I can break it out into a couple different areas. So there's one hot going to each of these SSRs, solid state relays. These are what enable the low power side of the board to actually turn the heaters on and off. So one of these wires coming in is a low current on and off signal for the relay. And then on the other side, we have our 2 hots coming in for our 240 volt circuit to actually deliver the amperage to the heaters. Then also coming out of this terminal block, we're feeding the DC power supply here. So for a little historical context, it used to be that 240-volt circuits, the wiring was just 3-wire. You had 2 hots at 120 volts each in the ground. The modern version of a 240-volt circuit actually has 4 wires. You'll have the same 2 hots and ground, but you also have a white neutral. And the addition of this white neutral enables you to wire in a 120-volt component into that 240-volt circuit. So what we're doing here is taking one leg of the 240-volt circuit, which is just 120 volts, and we're also attaching the white neutral and ground. And that enables us to power our 24-volt AC to DC power supply up here. And then from that, we're powering the microcontroller, which is on a shield board here. And then this little guy here is just an antenna that's coming off of the microcontroller for the Wi-Fi. And then we have our little breakout board here, which is doing a couple things. It's integrating the 1-wire temperature sensors, and it is also integrating some small amount of circuitry we need to integrate the flow sensor, which we'll look at in a second. Most flow sensors will deliver a rate of flow via like a variable voltage signal, so say 1 to 10 volts. Well, these Arduino boards can't handle a 10-volt input. The analog inputs on this particular chip are rated only up to 3.3 volts, so we add a potentiometer in here to basically linearly change that 0 to 10 to 0 to 3.3 so that we can read the flow without blowing up the board. Then kind of at the bottom here, we have the inputs we were looking at just on the previous slide. So we have our 2 pumps, and then we also have our kill switch over here. And then this thing in the middle here is mostly just a big terminal block for going back to negative DC. I have a couple other things just to distribute a 5-volt voltage here on the bottom, split out down there. So here we have one of the DC pumps and the flow meter. These flow meters are pretty nice. They're a little spendy, but you can configure them in a variety of ways, and they're relatively easy to integrate with control panels. The one caveat behind this particular model is it's not rated all the way up to boiling. It's rated up to about 175 or so, which is fine for our mash recirculation and sparge. But if we wanted a flow meter, say on the boil side, on the kettle side, we'd have to have something that could handle complete boiling temps. This will measure both flow rate as well as temperature, which is kind of nice because the way I have it hooked up is it actually turns out to be, like if we're recirculating the mash, this is going to be the temperature going back into the top of the mash, which is kind of nice to know in real time. Here's where it all comes together. Because of my chroma key screen, things that are green are showing up blue, so under the Brauhoff V4 title there, these are actually a list of the mash temps I'm stepping through. When they're completed, they turn green, and that's why they're appearing blue, because of the chroma key bug there. But you can see here's the representation of our hot liquor tank. And this is using a built-in hysteresis algorithm, so we can set a target temperature on it either manually or from a script. And then it'll just maintain that target temperature automatically with no intervention. It'll turn that one of the solid state relays we looked at earlier on and off to maintain that temp. And then next we have the mash tun temperature, and then our boil kettle on the left here. So we also have the representation of our two pumps here and here. And these are integrated in a way to where the valid range is 0 to 255. So we can actually change the rate that we're pumping relative to any desired flow rate, which is measured by our flow meter there. You can see here we're doing about 1.2 gallons per minute. And then we can also keep a running total. So you can turn pumps on and off based on a total goal. And you can also modulate their speed based on a desired flow rate, which is, of course, very useful for mash recirculation. So you don't recirculate too fast and compact your mash. And then also we have the temperature. As I was mentioning earlier, the flow meter can measure the temperature going through it, and that's what we're showing there. And then we also have explicit control over the kettle element here, and this is integrated in a way to where I can set the heater power down from 100%. You can't just run it 100% or you'll have a boil over. So once I'm boiling, I can just take this down to, say, 60% to hold the boil. Or you could also integrate this into a script where as soon as you are near a boiling temperature, you can automatically move your duty cycle percentage down to hold the temperature and avoid a boil over. And then, as I kind of mentioned at the beginning, I have an external script that will talk to Brewfather and will automatically migrate a given recipe into this table of mash steps. So that saves me the effort of having to manually type all these things in at the beginning of a brew day. I can just open another window and it lists all the active recipes I have in Brewfather. I can just say import. It'll bring all these temperatures and rest values in automatically. And let's see, over here we have, this is our countdown timer for individual steps. And then finally we have in the lower left corner, these are some of the scripts I've been working on for step mashing, automatically going through all the steps. And also a script that controls recirculation rate based on the measured flow rate, so that all turns out just right. So that's kind of that's what we can do. You build a panel like this, and you can set this software up exactly how you like to integrate all your components together and automate these things in a way that works for you. There's a lot of things out of the box, like the hysteresis algorithms, but anything that doesn't exist out of the box, you can just write a script to do, fundamentally whatever behavior you so desire. Right. So that's basically it. That's the overview of my hot side controller. This is still very much a work in progress. I still want to integrate more things. I'd like to get another flow meter that's also on the kettle side. And I think, as I mentioned or alluded to a bit earlier, I'm also working on integrating a new hot liquor tank, which is going to enable me to do some more things. So definitely more videos to come. Let me know in the comments if there's any of these particular aspects you would like to see me dive into further. One thing I could talk about more in the future is integrating individual components. It can be kind of tricky to integrate these things like flow meters that deliver different voltages than your microcontroller may want to accept. So that's definitely something that we could go into if there's any interest out there. So hit subscribe. Let me know what else you'd like to see. See you next time.